Hi, and welcome to our talk CDK for Terraform Deep Dive. In this talk, Daniel, Schmidt, and I are going to show you the technical stuff under the hood that enables the CDK for Terraform to work. And I'm Ansgar, as you might have read and seen, and I'm joined by Daniel Schmidt. And we are both senior software engineers on the CDK for Terraform team. And yeah, we are happy to show you some of the internals today. So, short intro to refresh. The CDK for Terraform allows you to define infrastructure in your favorite high-level languages. So like, for example, TypeScript, Python, Java, C#, and most recently Go. And under the hood, it works using Terraform. So you got all those Terraform providers and modules that are available to your power, kinda, so you can use them. And how that works is what we are after today. So let me give you some overview what we're going to cover. So first, we're going to have a short look at the CDK for Terraform stack in Python. And then we will see how we generate the Docker provider that is used there for TypeScript first, and then translate it to Python, and then execute the CDK stack, so that's the synth operation, and then to deploy the stack so that we have our infrastructure available. And yeah, let's start off with CDK for Terraform stack in Python. So this is a shortened example that you can also find in our docs. So what is defined there is the stack and some resources and Docker provider. So we're having the Docker provider at the top, then an image and a container. What this does is just run Nginx locally on your machine when you deploy it, but it serves as a simple example, and so we can cover more technical things easier. And what else is missing for this to work is the instantiation of an app and the stack, and then calling the synth method. And that's what we're going to get into later. And yeah, so what wasn't shown before, because I had to make the shorter, was the import. So we import from imports.docker. And that's something that's not available in the example that's generated. And how these bindings for providers, for Terraform providers are generated is going to be our first topic. So we are going to generate it in TypeScript for the start. This is an overview of what's going to happen under the hood, so you get a rough understanding, and I'm just showing you code after code. And to generate those provider bindings, we do CDK get. So that's a command from our CLI. And this is going to invoke the so-called constructs maker that we have something internally, and that can generate the code for providers and modules. So at first we'll get schema, so for providers via Terraform, and for modules via some utility library, and then it will generate the code. But let's just jump into it. So to specify the providers you're going to use, you put them into your cdktf.json config file under Terraform providers, for example. And for this Python example, use the Docker one. So we put there the reference to the Docker Terraform provider. And later on, when you run get, there's some constructs maker initialized, and that one is going to get some constraints. So in the end, that's just another representation of what we just put into our config. And then it's going to call generate method, or the CLI is going to call generate method on the constructs maker. And this is going to first start and invoke the generation for TypeScript, because all other languages are based on that, but that's something Daniel will get into later. And so this generate TypeScript method looks like this. So I've shortened it a bit, but you can see at the bottom there's some GitHub logo which just links to the source code. and yeah, you could see it in full length with all error handling there. But for the generate TypeScript thingy, it first will to jump into readSchemal, and that's where we are going now. So we are not caring about the rest of the code for now, so jumping even deeper. So if you remember, for the providers, the first thing at the bottom left will be get the schema via Terraform. So this is readSchemal, and it does both, so for providers and modules, but it's simplified for the providers now. So I removed all code for the modules, and this is the version for the providers only. And what it will do is it will create some temporary directory, and there it will write a main.tf.json file containing a definition of all the modules used, so that we can invoke the Terraform binary we have. So for example, it could be the one locally, with some init, and then Terraform under the hood will do its work and download all the providers. And then we invoke Terraform again with the command provider schema in the format JSON, and then we take this output and return it. So we get some schema definition for the provider that contains what resources, data sources, other configuration is needed for that provider. So let me jump into the version for the modules. For the modules, it's the same code, so it's also initializing it, so it's the same init, but this time it's not going to call something in Terraform, but it's rather going to call another helper method, which is called harvest module schema. So that one looks like this, and it's abbreviated, of course. It will look into a file that Terraform creates, so that's the .terraform/modules/modules JSON file, which contains information about the modules that Terraform downloaded, such as the temporary subdirectory where the module code is in. And then it will go in there and look for every file it finds for the modules and call this convert files method or function. And that one is imported from the helper library we have, which is called HCL JSON. And I'm not going to go into that detail now, but what it does is it takes all the HCL that is the code of the module in the end and converts it to a JSON representation so that we can use JavaScript magic to look into it and see what we need or how we would interface with a module or with this module. So back to the generate TypeScript one. We are now done with readSchemal. We've got information in this schema variable about the providers and the modules. And now we're going to do some data mangling. So I kind of commented that out. And then we check whether we have providers and or modules and instantiate Terraform Provider generator and or a new module generator. So these two classes will create the TypeScript code. They will just write a file to disk and have like add some method and everything to it. So that's something you could see in detail in our code base, but that's too abstract, not too abstract, but too concrete probably for this. So I skipped it, but instead I'm going to show you their input and the output. So we are treating it as a black box. So for the Terraform Provider generator, the input is what we got out of Terraform when we told Terraform to describe the providers in a JSON place. And we get something like this, which is heavily shortened. It was a lot longer. But for example, we can see there's an attribute to the Docker image resource, which is called name, and it's required. And if we now have a look back or forward at the output of the Terraform Provider generator, we can see that there's an image resource created, among others, and that one has some name attribute. And it creates some getters and setters and uses that in the synthesized attributes. So in the end, when we are going to interface with Terraform, we can get that information out again from the code in the high-level language like Python, TypeScript. And for the modules, it looks similar. So the input this time is a JSON representation of the HCL. so it looks a bit different. So for example, for this, I use the VPC AWS module or AWS VPC module, and it takes a name as an input, which is not required this time, but you can still pass it. And for example, among a lot of other outputs, it has the VPC ID of the VPC it creates that's going to get passed out of the module. So I choose those two, and now we're going to have a look at the result of a module generator. So what files it writes onto the disk in TypeScript that you could use in your CDK for Terraform TypeScript stack. And this looks a bit like this. So you can pass in a name, you can get the VPC ID output. So we suffix them with output to have no collisions with inputs with the same name. And I inline some function call what it does under the hood when you get an output. So it just returns the address that Terraform would use or you would use in Terraform if you want to point to some module. And yeah, synthesize attributes get some inputs. It's heavily shortened, but yeah, that's the gist. And well, now this is TypeScript, and I promised you Python. And so this is why I'm going to hand over to my colleague Daniel, who's going to show you how those Python bindings are created so that we can use the same thing to interface with Terraform in Python. Yeah, take it over, Daniel.
Thank you, Ansgar. Now, let's talk about how we get these TypeScript definitions over into Python, the language we want to actually use in this example here. We do this through a tool called JSII. JSII is a program that translates the TypeScript definitions over to Python, and at the same time it also includes a runtime that we use then to have like the communication done between different threads of the CDK program. So for a CDK program, the things that we actually manage in the end are constructs, which is a library also by the AWS team, and this library defines our infrastructure that we want to have as classes that sit in a tree, and these constructs can have side effects, and they can have and they can interact with each other. So that's basically what we want to get out of the run program. We want to have a tree of constructs, and let's take a look how that's done. So in general, we have the communication here between JSII and our program code, and JSII is run inside of a Node.js process and the program code in the language of our choice. That's where we need the runtime for. So we can see here the provider TypeScript definition. We have a image class here, which extends from the CDKTF Terraform resource. So our project's baseline is this Terraform resource that has some functionality in it that we commonly need. And you can see for the methods that we expose, we run this get boolean attribute or get string attribute method. This is part of our token system. So the token system keeps track of the references from values to another. For example, if you want to use this image here inside like a value of this image, for example, name, inside of our container later on, we want to have this in the end be a Terraform link, so a Terraform expression that links the image to the container. So we want to use like a reference, a Terraform reference here. So that Terraform then knows how to make this happen in the end and apply the code. If we move this over here to through JSII into Python, we can see all of this token system magic that we had before is gone, because the implementation actually lies in TypeScript. It's not in the generated Python code. Generated Python code just uses JSII get. We can see here for name and for latest to get the value from the Node.js runtime. So the Node.js runtime, in a sense, holds all source of truth here. And we typecast it and expose it to the user. So that's what the JSII wrapper code actually does. It's not that much. The main functionality lies inside of the generated code and inside of the contracts we write ourselves. So let's talk about how the execution works then. We execute when we run CDK tfsint. The synthesis command is there to translate from the CDK program over to the JSON that defines the spec of the like the Terraform spec. So that's the synthesis we have to do, and we do this by invoking the Python program first, because we need to get the information that you provide, like the user provides to us for the program and what the program should do. So this is run through the app command that we have in the CDK JSON. You can put in there whatever you want in general, but in the end, this all here for the CDK works through constructs, and we're gonna see how that works a bit later. When the code is executed here, for example, the first line would be now this Docker image we want to instantiate, so we give it a name, like give it the context, which is self, which is the stack we're currently in. We have the name of the Terraform resource, which is Nginx latest here. Then we have the name of the image itself. It's the latest version of the Nginx image. And we define that we don't want to keep it locally to the provider here. Under the hood, this actually triggers a create call through JSII. The communication here is done through stand in, stand out. You can find more on the official JSII website about how specifically this communication works, but we're going to go through the different forth and back between these two here now. So in this create method, we specify through the fully qualified name which resource we want to create. So in this case, the image from the Kreuzwerker Docker provider, and then the args we pass in. And it's the same as we passed, but as the underlying values. So in this case, the JSII by ref part here denotes that we have a reference here to a Terraform stack. So we could have a different Terraform stack here as well. If you have like 2 or 3 stacks for your application, those would be like different numbers here, different names. And for the second argument, we have a string literal that we can just pass over, nothing to be done with that. And the third one is actually an object. So this is in JSII a struct. And the struct has also like a fully qualified name. In this case, it's the image config. And then some data in it where you could find all the other literals we put in there. JSII does with that they work internally, so it builds a construct, it executes the Typescript code that actually builds the contracts to be precise, and then it gives us back whatever the Typescript code says. In this case, it says it's a reference, and it's a reference to this Docker image with this specific ID. So we got that created now. Now the interesting part is, what do we do when we have references between different parts of the code? For example, here in this container, we want to use the image that we previously defined. So we do in the Python code docker image.name. What does happen on the hood? So on the hood, we have Python that calls the get API of JSII and wants to get the name property of this specific object reference, which is the reference to the Docker image we declared earlier. And what we get back is a OK message again, so it worked. And the value here you can see is a Terraform reference string. I broke it a bit down so it's a bit easier to read, but in the end we want to have a Docker image with a specific name, which is part is the stack we have, which is Python Docker in this case. The other part is the name that we had, and the last part is a hash over the scope it's in. So if you define a different scope, for example, a different stack you want to define, or you have a different class that extends from resource and defines its own scope, those would be denoted differently. So we have a bit, we make sure that we don't have double identifiers here. So you are sure you can use the same variable inside of the same scope here. And yeah, that brings us everything we need to actually create the Docker container. So we can see here the create API is called again with the container. We get the stack from earlier, and in the struct in the container config, you can see that the image is actually passed. Or again, truncated because these things are pretty long, but you get the idea. The image from above is passed here, the Docker reference and the Terraform reference, and Terraform will later on resolve that and make the right deployment hierarchy out of that. Now we get back the container from the JSII code, so we get the reference again, and we're done with the program. It's not longer in this case. And now what's happening under the hood here is we want to have the HCL JSON, which is the same as here, like normal HCL, but in the JSON format that is easier to define by programs. How's that done? So we, as I mentioned previously, we have this tree of constructs that is created, and we like the most top level construct we have is the stack construct that you have to use, and the stack itself has a unsynthesized method. This unsynthesized method is called by JSII to ensure that side effects will happen. And the side effect of these stacks is to create this this HCL JSON here. We do this by traversing the entire tree that we have of items, the entire graph of these constructs, and we call on each of the parts of the constructs a toTerraform method that we define that serializes the data down, and these are all combined, and in the end we get this HCL JSON. So you can see here in the beginning we have the required providers here. This is part of the CDK JSON, and it's inline here. So the entire file is like the only thing you need to deploy is this one file, and Terraform will know everything around that by just getting this one file. We see we have also like providers key that defines the Docker provider, and if we want to pass some parameters down to the provider, we could have done that and they would be here. And we have some metadata in the beginning just for us to know which stack this is, which version, and next we need the resources. So we have the Docker image here. You can see this long identifier we had earlier is used here as the key for this Docker image, and all the specification is on that level, and again with the double slash we have the metadata again that gives us an idea around where the thing is in the call hierarchy and what the unique ID is and so on, stuff we could need for debugging later on. And last but not least we have the Docker container, and you can see here that the Terraform reference string is used again. So we have the reference made from the image to the container. So Terraform will know when deploying that it has to first deploy the image and then the container. And that's how the internal communication is done. So Ansgar, how is this actually deployed in the end?
Yeah, thanks Daniel. So let's see how we can deploy the stack. So we now need to interface with Terraform and do a bit more magic maybe to get this written config into the cloud, not the config, but the resources provisioned in the cloud. So what we're now going to do is we're going to have a look at CDK deploy, and that one is going to first check which stack, as the CDK for Terraform allows multiple stacks, which stack is going to be deployed, and then it's going to invoke the Terraform CLI, and yeah, let Terraform do the work for us, so we don't have to reinvent the wheel, kind of. So let us first look at the starting point for determining which stack to deploy. So when the synth is called or runs, there's also in your output directories like cdktf.out a manifest.json file written. For our simple example, it just contains a single stack, Python Docker, but it could contain more. And here we can see the synthesized stack path, which points the CDK for Terraform to the direction where the cdk.tf.json file is. And we need to tell Terraform to deploy this, or the infrastructure which is in that file. And when you invoke the CLI command, we do one more thing. So we also determine where the Terraform invocation is going to happen. So for example, if in that stack is a remote backend defined, that would be, for example, Terraform Cloud, we would check whether the Terraform Cloud workspace is a remote one, so with remote execution. And what this does is it wouldn't run Terraform locally on your machine, so the process, but rather in Terraform Cloud. And depending on that, we set our internal Terraform that we're going to use. The alternative is using the CLI one, so the locally installed Terraform, what you normally do. So I'm going to go with that. And yeah, let me proceed. So at one point we have this Terraform, which is now a wrapper for our CLI kind of, and we're calling the deploy on it. We're passing a plan file. That's something that would happen previously. We would need to look into the source, and it would, yeah, there's a lot more happening. But the gist of it is we're going to invoke this deploy, and we get some updates so that we can show in the UI when some resources are updating or finished updating or creating. And yeah, by this, let's have a look in the to the concrete implementation of this deploy. So the deploy for the Terraform CLI is going to invoke the Terraform binary that's available locally, and it's going to do a Terraform apply with autoproof set, because we ask our user first if he's sure that he wants to deploy that infrastructure. And so we're setting autoproof so Terraform doesn't ask again. And then we're also passing state file options, so that's information we have where Terraform has its state, because that's different for the different stacks. That's something CDK CLI handles. And also the environment for the process is put in this spawn of the subcommand. So for example, you could set some TFR environment variables and they would work in that stack. And yeah, let's look further as this is it. So now it's after you invoke Terraform, the resources are in the cloud and you're done. And by that, I gotta thank you, and or we gotta thank you for being with us today. And yeah, I hope you liked it. If you have any questions, ask us. If you find any issues, file bugs, check out GitHub, check out HashiCorp.learn, where you can learn more or do some guides to get started with the CDK for Terraform. But as you've heard this deep dive, we suspect that you have some prior things that already happened with the CDK for Terraform. So yeah, thank you, and yeah, have a nice day.